Analytical cartography employs methods from different disciplines to make maps, to do spatial analysis. These methods, including computer science, mathematical methods, and statistics, cartography itself, of course, is a method, right? And also psychology, because when we're trying to design a map, we need to know what people think, how people perceive, right? That's psychology. And also there are different topics, typical topics included in analytical cartography. And I'm going to introduce them one by one, very generally, okay? I'm not going to go deep. So the first topic is map transformation, and it's another word for map projections, right? So what's the definition of a map projection? It's a mathematical transformation from 3D real world to a 2D surface, or you can say this 2D surface is a map, right? Here we have 4 maps of the United States mainland, and they have different shapes, right? Because they are using different projections. That's the very foundation of map making, of cartography. You need to choose a map projection before making a map. The second topic is sampling, right? When we have a data set, we don't usually use all the data records, especially when the data set is very huge. So we need to pick some of the records, and this process is called sampling. And there are a lot of literature and telling you or proposing different sampling methods, because different sampling methods could lead to different spatial patterns, and beyond that, different conclusions, especially when you are doing sampling at different scales. And this phenomenon is called MAUP, which means that when you're sampling at different scales, you will probably have different spatial patterns from which you can draw different conclusions. So sampling is very important when you are trying to deal with a subset, when you're trying to choose a subset of a data set and make maps beyond that, based on that, and do spatial analysis and then draw a conclusion, okay, sampling. And then map generalization. This usually happens when you are downscaling or upscaling maps. So here we can say there are 2 linear features showing the same river, but the top one has more details in terms of the shape of the river, the direction of the flow, while the bottom one has less details, right? Sometimes when you're trying to show a geographic entity such as this river at low scale, for example, county level, the top one would be your choice because you want to show more details at a lower level, at a lower scale. But when you're trying to show the same river at state level or even national level, obviously it's not necessary and there is no space for you to show so many details. So we do map generalization to have another linear feature representing the same river, but with less details. It's good enough. It's good enough, right? So map generalization. And then we have different data models and data structures to show our geographic data in a map. So generally there are 2 types for data models. On the left side, we have vector model. On the right side, we have the raster model showing the same linear feature. Let's just say it's a river. On the left side, it's our natural perception of a linear feature of a river, right? At each segment, there is a specific direction, there is a specific length for this segment, and multiple segments, when they're combined, we have this line feature or linear feature showing the river. On the right side, we have raster model. In a raster model, the whole space is divided into a lot of small cells. Each cell can have multiple states or simply two states, 0 or 1. If a specific cell is occupied, it is painted black, which means it's 1. If this cell is empty, nothing is there, there's no river in this specific case, then it's 0, it's empty. Okay, so use zeros and ones. We can portray this linear feature or this river using raster model like this, right? And of course, beyond that, you can just show polygons or aerial features using two models, right? On the left side, we have 1, 2, 3, 4, 5, 6, 6 polygons within the area, and we're using vector model to show these 6 polygons, and they're separated by linear features. On the right side, we're trying to show the same 6 polygons, but using raster model. Here, we cannot use linear feature to separate them, to differentiate them. We use cells with different values to show these 6 polygons. For example, polygon 1. All those cells occupied by polygon 1 is given. Each one is given a specific value. That specific value is 1. Right? So all those cells with value 1, they form the polygon 1. Then we repeat this process. We gave 2, 3, 4, 5, 6 these values to different cells to form different polygons using a raster model like this. Okay. So next, another topic very important in analytical cartography is called analytical visualization. On the left side, we have a remote sensing image showing an urban area. So all the pixels, all those, you can see all those buildings, roads, vegetation in real color. But sometimes this is not enough. This is a visualization, of course. But it's not enough. We want to do more analysis. For example, we want to differentiate different land cover types within the area. So we need to use analytical method to produce analytical visualization, such as the one on the right side. On the right side, we have different colors. We have small patches. And the different colors are for different land cover types. This is analytical visualization after analysis. And this analysis specifically here is called classification because it's remote sensing. We use classification methods to differentiate different land cover types. For example, in this visualization, we have grains. We have dark grain, light grain for vegetation, blue for blue roofs and water, gray, different gray scales, gray, different levels of gray. They are for the road. They're for the road. They're for the road, and other materials. We call them impervious surfaces. For example, this white area is also roof. Okay, roof is impervious surface. Could be metal, could be concrete, right? And we have asphalt also as impervious surface. So we can see here different roads. They are portrayed in gray. They're portrayed in gray. So original image, right? Original visualization, and on the right side, analytical visualization of the original visualization. And Franklin, in his paper of 2000, he, how can I say? He addressed different applications of analytical cartography, including terrain visibility analysis, map overlay, mobility and routing, interpolation on terrain surfaces. Let's just see some example of these applications of analytical cartography. First one, terrain visibility. So here we have a mountain colored by orange. So we have another 3 points, green points red point, green point, red point, and blue point. You can consider that you're standing at green point, at red point, or at blue point. Since this is a mountainous area, when you are standing at different points, the visibility of yours is different. When you're standing at green point, for example, you can only see objects within yellow areas, right? On the left side and on the right side. And beyond yellow areas, you cannot see anything. It's the same thing for blue point, for red point. This is called terrain visibility. We analysis visibility based on specific terrain. You will say, what's the application of this? A typical application for this is signal tower building. When you're trying to, for example, you're an engineer from AT&T, you're trying to build a signal tower within this area, so it can cover the largest possible area within this region. See that, right? So where do you want to build the tower? You want to build the tower at a location with the maximum visibility, because the travel of telecommunication signal is just like the optical light. If you cannot see something, it means that something is covered by another object. In this specific example, by mountain, right? So the best area, the best location for the signal tower might be here at the top of the mountain to get the maximum visibility, right? So that's terrain visibility. So next one, map overlay. This is application of cartography when you're trying to overlay 2 or even more maps. This is an example why map overlay is important. We have 2 boundaries here. One is in red, another one is in black. For example, let me tell you that these 2 boundaries, they are for the same enumeration unit. Then you would ask, why do we have 2 of them? Because they were collected at different years. And for example, the red one was from 1990. The black one was from 2000. In these 10 years, the boundary of this enumeration unit changed. Let's ignore reasons first. Let's just say it changed. When you're trying to overlay 2 maps covering the same area from 2 years with different boundaries, how do you address the actual boundary after overlay? Well, there are different methods. You can just use the middle line between these 2 boundaries to represent, to address the boundary in your map. And there are different methods. And this is pretty important because when we're dealing with census data, the change of boundary is very common, right? When you're collecting data from different years and you want to make 2 maps and then overlay these 2 maps, you will face this problem. Okay, I can tell you that there are a lot of literatures addressing the same problem using different methods and algorithms. So it's pretty important. And the next one, mobility and routing. This is a very important area for GIS. And what does it mean? So you may have heard this problem before. It's called traveling salesman problem. What does it mean? It means that a salesman is going to travel around the country. He's going to travel all cities in this country and get back home. So the problem is, what's the shortest distance he travels to finish this trip? Okay, so this is traveling salesman problem. For example, I have a very simple case here. Assuming that this salesman is living at city A. is going to travel to city B, D, C, or any or in any order. But anyway, he will travel all the cities and get back to A. And the figures here, the numbers here, they are representing the distance between two cities. So I would ask you, what's the shortest distance to travel all the cities and get back to home? So in this very simple case, you may use a pen and a piece of paper to calculate, right? To enumerate, I mean, to exhaust all the possibilities and choose the one with the shortest distance. But we only have 4 cities here. How about 400 cities? How about 1,000 cities? You cannot use your pen and piece of paper to do that. You need to rely on a GIS system, to a specific algorithm to find out the result for this. Okay, so this is about mobility and routing. Its application is pretty wide. For example, you're trying to divide a bus system for a specific city. It's a similar problem, right? Obviously, distance is one of the most important factors you need to consider when you're trying to design a traffic system, such as a bus system. Okay, so the next application is called interpolation on Terran surfaces. So interpolation means using known data to predict unknown data, right? For example, we have sample points. They are represented by orange crosses. But how about this specific location with a question mark? It was not measured, but I want to know the value for it. So you need to use known points to predict it. Why is this important? Because usually in remote sensing, for example, this is a DEM image showing the different elevations at different places. Usually when we're sending people to the field to what? To collect data, to collect elevation data, we cannot sample too many points. At the end of the day, you may have sample points like this orange crosses. But in order to produce this very smooth surface, we need to add more points between sampled points. So this, in this case, we need to do interpolation to use sampled points to predict unsampled points, right? So this is interpolation. So I will just stop here and I will see you in the next part. Thank you.